In 2019, Unit 6, the student investigate how the time period vary with time period of a simple pendulum vary with the length of a pendulum using the apparatus. So as you can see, the pendulum is vibrating. The time period of a pendulum is given by a formula t equal t pi and t equals 2 pi under root L divided by g. State a reason why using a small displacement. The student displaces a pendulum by a small distance to set up a pendulum oscillating, and student measure the time for the oscillation. So normally, because when we say that time period is only affected by the length, this formula is derived on the assumption that the theta is very small. The derivation of this formula involves one assumption that theta is very small, that the value of the theta and sine theta are equal. So if we take a large amplitude, that case what happens, the amplitude, if it's larger, so value of a theta is more. If value of the theta is more, so this relation cannot be no longer valid. That's why student is using a small displacement. So basic idea is that because this equation is only derived when theta is very small and value of the theta is equals to sine theta. The student use a pin as a timing marker. Explain how placing a pin at the center of oscillation would lead to more accurate value for 10 oscillation or 10 times vibration. So what might be a reason for that? Look, this pin is there at the center and it is oscillating to and fro. How a student can ensure that the time period is measured accurately as possible, and the identification point, what student consider the identification point, that is the center. So why it is accurate, like what is the advantage of marking this position? Because when this pendulum is vibrating, you don't find any reference point. There is no reference point. For example, when a pendulum is vibrating, if it starts from position A and we leave this pendulum, so it will vibrate in opposite direction and then return. But the problem is it won't return back to the same original position, because whenever pendulum is vibrating, it loses some its energy, so it will not return back to the same position. It will return to a new position, and then every time the position will change, so it won't be accurate. That's why the reference point, why the center point is taken as a reference, because every oscillation, every time the pendulum will pass through this point. Why not any point in the amplitude we take? Because not every time it will reach that point. That's why it won't be accurate. So when students start the timer, like he started the timer, when he released the pendulum was there at the mean position. The student displaces the pendulum to extreme position and then release. But when student release, student did not start the timer here. Student start the timer when it reaches the center position or the pin. What is the reason for that? Because every time when it vibrates, so he start the timer here. So this is going other side, then to other side and returning where. That's one time. So every time it will pass through this point. But why not the starting point, the extreme position? Because this pendulum will lose its energy. As it will lose its energy, it won't return back to the same original position. So it won't have a correct reference. When student obtain the value, complete the table. So this is the time, mean time for 10, and then for time period. How to get the mean? You have to take an average, like add them and divide it by the total number. But keep one thing is in mind, that anomalous, you should, if any of the value appear to be anomalous, that you should remove from the result. So 10.2, 10.24, 10.28, 10.32, and 10.15. So when we add them, we can average of this. So 10 point, because all the values are two decimal places, so we should write 10.238 is a average, but because all the values are two decimal places, so this should be two decimal places as well. And then mean, how to get the mean or average? So for one time period, this is a time for 10, so you need for 1, so you divide by 10, which will give you 1.02. That is the mean time. Then calculate the percentage uncertainty in T. So how to calculate the percentage uncertainty? The formula to calculate the percentage uncertainty, when you have a group data, that is a maximum minus minimum divided by 2. So whenever group data is there, the formula for uncertainty is equals to maximum minus minimum divided by 2. The maximum value in the group data, it is 10.28, 10.32, minus minimum value is 10.15 divided by 2. So this will give us the uncertainty in the measurement. And then to calculate the percentage uncertainty, so this is 0.085. That is the uncertainty. What is the percentage uncertainty? Percentage uncertainty is the uncertainty 0.085 divided by value recorded. What is the value we record according to the question? Basically the mean. So the average, what we calculated, that was 10.24 into 100. So it will be about 0.83% uncertainty. The next part, the student double the length. He made the following prediction that if the time period of a short pendulum is Ts and the double length is Td, so then Td square over Ts square should be equal to 2. Justify this prediction. So we have the formula T is equals to 2 pi under root L over G. Look, 2 is constant, pi is constant, and under root G is constant. So I can also say that time period is directly proportional to under root L. That we can say. Or we can say T square is proportional to L. And whenever two quantities are directly proportional, their ratio is constant. So T square over L is equals to K. So I can say T1 square over L1 is equals to T2 square over L2. Like if first pendulum length is L1 and its time period is T1. Second pendulum length is L2 and its time period is T2. So example, if the time period of and the length of the short pendulum is L, so Ts so T is equals to 2 pi under root L over G. So Ts square over L is equals to Td square over 2L. Why 2L I write? Because I mentioned that is double length. So its time period is Td and length is 2L. When we simplify, because we want TD square. So we cross multiply, 2L will be multiplied, and this will be TD square over TS square. So when we simplify, length will cancel with length. So we can say T is equals to TD square divided by TL square. Is it clear? Then the student determine the time period for a longer pendulum, and that is 1.46 into 10 1.46 plus minus 0.011 second. Determine whether the result supports her prediction. So she got this result, and whether results support this prediction, like this is a time period for the second pendulum, which is the length is doubled. So whenever you want to calculate, whenever you want to identify whether the results are correct, so we can calculate, we can compare the percentage uncertainty with the percentage difference. That is one way. Or we already worked out that the time period for a short pendulum, this for long pendulum, double pendulum is 1.461, and for short one it was 1.02. So if we substitute the according to prediction, when we divide them, it should be 2. So TD square over TS square should be equal to 2. So we'll substitute the value for TD square. So TD square over TS square should be equal to 2. So TD, that is a double longer pendulum, that is TD. So 1.461 square divided by 1.02, that was in the mean which we took or calculated in the first part. So TD square over TS square, when we divide them, 1.461 square divided by 1.024, 4 is also there. So this is about 2. And what about the uncertainty? Because basically, like, this is about 2.04. And what was the uncertainty in the measurement? The uncertainty measurement of a time period is 0.83. So either we will be 0.83 more or 0.83 less. Like the value which we obtained, either it will be 0.23 more will be there, 0.83 more will be there, or 0.83 less. So when we calculate, and we already calculate the uncertainty in this measurement, that was 0.83. So if we consider the uncertainty in the other value, the smallest value here, and it will have a smaller limit when TD square is less and TS square is more. So we already know, like, what could be the values for TS square. So how to identify the maximum and the minimum value of TS square, because we know 0.83% uncertainty is there. So adding 0.83 plus 0.83% of this will give us a maximum value of TS, and subtracting the 0.83% will give us the minimum value of TS. But what about the maximum and minimum value of this one? So how to get the maximum value? So we should know the answer, or we already know the uncertainty. So maximum value will be 0.011. So 0.011 of this will be the maximum value. Like if this is added, this will be the maximum value, or it will be minus 0.011 second. That will be the minimum value. Now to know the upper and the lower, like this is according to value which we get 2.04, but this value might be more, it might be less. So how to work out that? What will be, how we'll know what will be the maximum value and what will be the minimum value? So if I know the uncertainty in both measurements, and using, because this is TS square over TD square, so their uncertainty, whenever there's a square, uncertainty will be doubled. So using that, we'll work out what will be the maximum and minimum value or uncertainty in this answer. So how to know the uncertainty in this answer? So like uncertainty in this value. So how to know uncertainty in this value? Uncertainty in TS is 0.83%. But because it is S, square is there, so it will be double. Like what power is there? Uncertainty. If power is square, it will become 2 times. If power is cube, it will be 3 times. Power 4, it will be 4 times. And what about TD? So first we should calculate the uncertainty. That is 0.011 divided by value recorded 1.461 into 100. So uncertainty is 0.75. So there is a 0.75% uncertainty in this value, but it should be multiplied by 2 also, because that is TD square. So what is the uncertainty in this one? That is 1.5%. And what about the uncertainty in this value? That is equals to 0.83 times 2, 1.66. So one is 1.66, one is 1.5. So when we add the two uncertainties, so that is 3.1. So means this will have an uncertainty of 3.16%. Means the value might be 3.16% more. Actual value might be 3.16% more, or it might be 3.16% less. So we'll check if the 3.16% of this one, so 3.16 times 2.04 and divided by 100, that is 0.06. So minus 2.04 equal to 1.97. So means if this value, which is 2.04, what will be the upper limit? The lower limit will be 1.97, and the upper limit, like the highest value which we can have, 0.06 plus 2.04. So highest value will be 2.1. So means any answer within this range is acceptable. Is it clear? So this was question 1. That was the last part. Yeah, that was the last part. And next is doubt is question 2, 1, part 1 and 4. Explain how EMF is induced in the secondary coil. You have to explain the working of a generator here. An alternating current in a primary coil generate magnetic field, the transformer basically. Like we have in a transformer, what happened? There's a primary coil and there's a secondary coil. An alternating current produce change in magnetic field which induce EMF in the which magnetize the iron core, and change in magnetic field of iron core induces EMF in the secondary coil. Explain how EMF is induced across the secondary coil. So basically a basic idea, like there is a change in magnetic field, as we have an alternating current which produce variable magnetic field, and due to change in magnetic field there is an induced EMF in the secondary coil. You can use the term magnetic flux linkage as well. That is the same thing. So you have to explain the working of a transformer here. Then student uses the apparatus as shown. So two coils are there. EMF is induced across the secondary is given by a formula KNI over DQ. A circuit to show how primary coil should be connected with an additional component. So what we want, I is the current in the primary. So this is a primary coil. And to draw a circuit diagram, what is the circuit symbol for a transformer? The circuit symbol of a transformer is like a coils. And if it is a step down transformer, like secondary is having more turns, so then there will be an ammeter as a because why I connect an ammeter, because we want to measure current in the primary, and there should be an AC supply, alternating current supply. So this should be the circuit which we should use. Then the next part, that is 2B4. Statement of a significant source of uncertainty. Look, what might be a source of uncertainty in this example? You're measuring a current. When you are measuring a current, then you may have a parallax error. Then the things which you are measuring in the question, you are measuring D, because student vary V and D. V is a voltage and D is a distance. So uncertainty in measurement of the distance, because look, there is no reference point. Like this is a hollow. This part is hollow, so we cannot exactly identify that whether the scale is placed at the same position as in the first man. Like whether all the time distance from one coil to another is measured from the same references within the coil, because coils are hollow, so we cannot identify, so that measuring a distance will lead to uncertainty as well. So difficult to measure or uncertainty in measurement of a distance between the coils, as they don't have any fixed position. In 3B, the surface temperature, this is about radiation flux and wavelength. Suggest two reasons why the lambda max might not be accurate. Look how you're measuring a lambda max, as you can see here, radiation flux variation. So what might be the reason why this lambda max, when we are measuring, is not accurate or it is not correct? So when you plot the graph, draw a line of a best show where the radiation flux is maximum. Look what we did. When you draw the line of a best fit to work out where the radiation flux is maximum, but why it is not accurate? Or number one, that you don't have too many values, too many results around the maximum. Whenever this type of case is there, when we have to intersect the two lines, so we should have more result or more values in this region, but we don't have too many values. We are just predicting. That's why it is not accurate. So there should be And here the line of a best fit, it is not exactly straight because it is slightly curved. So line of a best fit, if it is straight, then it will be more accurate as compared to this one. And we are not repeating the values near the maximum. That's why it leads to error as well. Then question number 4A. A student investigated the absorption of a gamma radiation by a lead using the apparatus shown. She recorded and corrected the background counts. Explain why it is possible to correct for background counts. So because it's an alpha, so like as you can see in the question, absorption of a gamma radiation by a lead. So thick lead is there. How we can use, or how we can say the correct background counts in this one? Because if there was no source, the radiation will enter the GM tube even there is no source. Every time, same amount of difference will be there. Like example, if I say on average, if I say background count is 30, if the total count, the rate meter is representing 150, so how many, what will be the reading from the source? So it will be 150 minus 30 equal to 120. Same thing if the reading changes to 120. So again, we'll subtract 30. So 120 minus 30 is equal to 90. Then it is example 70 minus 30 is equal to 40. So every time we have to subtract the same number. So it means this is a systematic error, and systematic error, it arises due to the constraint in the system, and either to reduce the systematic error, either we have to add a value or we have to subtract the same value. So the question is, like, why she recorded and corrected the background count. Explain why it is possible to correct for background counts rate. Like why we can correct this like how we can get the radiation from the source, how we can correct the background counts. It is obvious that every time when the radiations are coming out, they come out with an extra, example 30 background or 35 or 32 background. Every time it is there. So it's easy to just remove the value from the original to get the corrected backgrounds. So you can mention every time there is the same amount of background, on average it's the same amount of background radiation, which leads to a systematic error. So we can correct for the corrected background counts or corrected counts, we can just simply subtract the same number from all the readings. If it was a random error, like sometime reading is more, sometime reading is less, that time we won't be able to correct these background. We won't be able to put the corrected counts for the background and the source.